Hi everyone. In this video lecture, we're going to be talking about economic interest, which is the amount of money earned or owed on an investment or a loan. The investment or the loan itself is called the investment or loan itself is called the principal, or the amount of the investment or loan is called the principal. We're going to look at three different ways that economic interest is calculated. The first is called simple interest. Now, let me give you an example. Let's say I take a loan of $100. That's the principal. The interest rate is 5% per year. And I hold the loan, so the term is 4 years. To calculate simple interest, you have the loan amount, the principal, the interest rate as a decimal, and the term. And then the interest itself, we calculate by taking the principal times the interest rate times the number of years. P times R times T. So in this case, 100 times 0.05 times 4 is $20. Now the interest is not what I pay back. I have to owe I have to pay back the principal plus the interest. Obviously, if I take $100 out, I need to pay back the $100 plus the 20. So the principal plus the interest in this case is $120. And that's how you calculate simple interest. There are loans that work like this, where you have a fixed amount, an annual interest rate, and a loan term, and you're just expected to pay back the principal and the simple interest at the end of the loan. Simple interest is fairly straightforward. There's not a lot of calculations to it. It's not really exponential in any way. So now let's talk about the second type of interest, which is exponential. Compounding interest. So in this case, let's take a $100 loan. The interest rate is 5%, but it compounds every year, which means the interest is calculated on the loan every single year that I hold the loan, and the term is 4 years. When we do this, we're not going to be calculating the interest by itself. We're actually going to be calculating the balance of the loan in each year, as opposed to just the interest on the loan itself. So if I want to know how much is the loan worth in, or what's the balance of the loan right at the beginning? Well, no interest is accrued, so it's $100. Now, after 1 year, I'm going to take that balance and I'm going to add to it that little bit of interest, which is 100 plus 0.05 times 100. But I'm going to rewrite this. Notice I have 100 here and 100 there. So that's actually 100 times 1.05. 100 plus 0.05 times 100 is 1.05 times 100, which is $105. Now, in my second year, when I apply the interest, I'm not going to be applying it to the original 100 because my new loan balance is 105. So I'm going to take that 105 plus 0.05 times 105, which is 105 times 1.05. And notice as I move from year 0 to year 1, I multiply by 1.05. And as I move from year 1 to year 2, I multiply by 1.05 again. Desmos will tell me what that number is. And it is 110.25. In year 3, I do it again. I take the 110.25 and I multiply it by the 1.05. And really what I'm doing, since I've multiplied it by 1.05 3 times, I'm taking the original principal and multiplying it by 1 plus the interest rate cubed. And this is my exponential growth. I'm taking my original balance, and every year I multiply it by 1.05. So by the third year, I've multiplied it by 1.05 3 times, which is, according to Desmos, 115.7625. And then I do it one more time in year 4, which was the original balance times 1.05 to the 4th, which is, according to Desmos, 121.55. So 121.55 and some fractions of a penny. Compounding interest takes your balance and multiplies it by 1 plus your interest rate every single year. And so it's going to grow in a compounded way. And notice 121.55 is bigger than the 120 I got from simple interest because it's compounding every year. Let me switch to the next page because I can still pull off the after 4 years, the balance is $121.55. So I can still get the principal and the interest. When I pay it back, I'm paying $100 on the principal and 21.55 in interest. So I can still find out the interest after 4 years, but the calculations I do give me a balance, which then I have to convert to find the principal and the interest. Okay, now that is compounding every year, but we can also compound using a shorter timeline, like months. So let's take a loan amount of $100. Let's take an interest rate of 5% annual, but we compound monthly. And the term of the loan will be 4 years again. I'm going to show you the formula for this rather than build it out of the table because it's a bit more complicated. So the balance, and again, we calculate the balance here at time t, is going to be the principal times 1 plus the interest rate divided by the number of compounding periods raised to the number of compounding periods times the time. This is kind of dense, so let's pull it apart. So the balance at time t of my loan is going to be $100 times 1 plus 0.05 divided by 12. Months means I'm compounding 12 times per year. And then I take the number of years and I multiply it because I'm compounding 12 times per year. So we divide the interest rate into 12 pieces and we compound 12 times. 5% interest rate divided into 12 pieces because now we're compounding every month. I can't do 5% every month. That would be way too high. So I divide it by 12. But since we're compounding every month, after 1 year, I've done this 12 times. After 2 years, I've done this 24 times. So now let's build our table. Let's see if I have space. There's my formula. So we'll have T here and the balance over here. Well, again, at the beginning, it's just a $100 principal. After 1 year, I take that $100 and I compound it 12 times. So Desmos will tell me what that is. I'm typing it in right now. I know you can't see this. And it's $105.17. Notice that itself is bigger than compounding once per year. And after 2 years, I take that 100, 1 plus 0.05 over 12 to the 12 times 2. Now I've done it 24 times. $110.49. It's growing faster than when I was compounding it once per year. And let's look again at 3. That's going to be 36 compounding periods. But the year is the one that goes into the function, and I get 116.15. And after 4 years, I end up at 122.01. No, 0.09. Which again is more than when I compounded it once per year. Banks definitely do this. Other lending agencies might. You just have to be able to piece apart this kind of clunky formula where you take your annual interest rate and you divide it into 12 pieces if it's monthly, 365 pieces if it's daily, and then you compound it not once per year, but 12 times per year if it's monthly, or 365 times per year if it's daily. So I've used loans so far because loans often use these type of terms. Maybe it's simple interest, maybe it's compounded once per year or once per month. Interest rates on investment accounts are usually different. So investment accounts usually compound or grow continuously. So it's not once per year or once per month or even once per day. It's with computers, it's like once per millisecond or picosecond. And as soon as we compound continuously, we use the natural exponential base, because the natural exponential base E is the number that represents continuous growth, continuous exponential growth. So this is our third type. It's continuous compounding. Loans generally don't work that way, just because they tend to have like contract terms. But if you put your money in a bank, there's not like a contract. They just offer you an annual interest rate with continuous compounding. And the process for this is the balance. Let me start with, we still have a principal. So let's say that's $100. We have an annual interest rate. Let's say that's 5%. And we have a term. Again, if it's investment accounts, it's usually not like a fixed term, but let's just look at number of years. So if it's an annual interest rate, then number of years is what we want for our term. And then the balance at time t is the principal times the exponential, natural exponential, raised to the RT, where R is the interest rate as a decimal, and T is in years because it's an annual interest rate. So in my example, the balance at time t is going to be 100 e to the 0.05 t. And it's as simple as that. Okay, let's look at what the balance would be on an investment account where I invest $100 at 5% annual interest rate, compounding continuously. Well, at the beginning, it's 100. After 1 year, it's 100 times e to the 0.05, which is about 105.13. After 2 years, it's 100 times e to the 0.05 times 2, which is 110.52. These are approximate now. Natural exponential base is never going to give you exact answers when you put decimals or whole numbers in. After 3 years, e to the 100 times e to the 0.05 times 3, which is 116.18. And after 4 years, 100 times e to the 0.05 times 4, is 122.14, which is the largest of all of them. The natural exponential base will give you, with a general annual interest rate, if you compound continuously, you're going to reach the largest numbers, but not by much. This one was 112. Sorry, 100, why did I write 112? It's 122.14. And the monthly compounding was 122.09. So there's not a lot of difference. So these are the three types of interest rates. You have simple, compounding, and continuously compounding. All right, now that we have these different types of compounding, we can start asking questions that involve them. So, for example, all right, I'm going to actually do one of the questions from the lab manual because I think this question is kind of hard to pick apart, and I'm hoping that you can come into class with some understanding of how it works. So if I have $10,000, let's keep it simple, $100, and invest it um, at for 6 years at an interest rate that compounds daily. What rate do I need to reach $150 after the 6 years? So when you solve these sorts of questions, the first thing you should ask yourself is, what type of equation is this? It's going to be a compound interest equation because it compounds daily. So now let's set up our formula and just remind us that the balance at any time x is the principal times 1 plus r over n to the nx, where r is the interest rate as a decimal, and n is the number of compounding periods. So b of x in this example should be 100 times 1 plus, well, the interest rate is what I don't know. I'm going to leave that as r. But I know the compounding, which is daily, so 365, raised to the 365 times x. Now, x is the number of years. I know that. It's 6 years. And the balance should be 150. So I can fill in a little bit more information. I get 150 equals 100 times 1 plus r over 365, all raised to the 365 times 6. And now I have an equation where I'm trying to solve for r. This is not an exponential equation because r is not trapped in the exponent. So I want to make that clear. This one is not exponential because r is not up here in the exponential part. But I can still solve for it. The first thing I'm going to do is I'm going to find out what 365 times 6 is. Just so I'm working with numbers when possible. $21.90. And now I'm going to solve for R. Let me switch to another piece of paper. Solve 150 equals 100 times 1 plus R over 365 raised to the 2190 for R. So I'm going to divide both sides by 100. That's a good start. And I get 1.5 equals 1 plus R over 365 to the 2190. Now R is trapped inside of a power. So to do that, I need to undo raising to the 2190, and I can undo it by taking the 2190 root 1.5, which is kind of ridiculous, but that's what you have to do. Because if I raise it to a 2190 and then I take the 2190th root, that will cancel. And I get 1 plus R over 365 over here on the right. Now, how do you do this in a calculator? The easiest way to do it is to, instead of as a root, raise it to the fractional power. When I start that over, 1.5 to the 1 over 2190 should equal 1 plus R over 365. Desmos can do that no problem. 1.5 to the 1 over 2190 is a number very, 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 very close to 1. And so you need to keep track of lots of decimals here, or else you're going to lose precision before you're ready for it. So that's that 1.5 to the 1 over 2190, which equals 1 plus R over 365. And I continue solving for R. Let's subtract 1 from both sides. So I get 0.00018516103 equals R over 365. And then I multiply both sides by 365. And fortunately, I got a calculator to do all of this work. 0.06758. 0.06758. If I'm working in interest rates, I bet 6.8% is probably close enough. And that's how you solve for the interest rate that you need. So even though the idea of this question involves exponential equations, the actual solution doesn't. So let's solve for one that does involve solving an exponential equation. So let's see, I invest $200 for 5 years. What interest rate do I need to reach $260 at continuously compounding interest? So again, we start by asking what sort of equation am I working with? I'm working with continuously compounding interest. So I'm going to remind myself what that looks like. The balance at any time is P times E to the R X. E is a number, about 2.718. So let's fill in what I know. I want to reach 260. I start with 200. I don't know my interest rate, but I do know that I'm compounding for 5 years, or I'm investing for 5 years, sorry. Or maybe I rewrite this as 200 times e to the 5r. Aha, to solve this, I have an exponential equation because the r is trapped in the exponent. So I first isolate the exponential, divide both sides by 200. I get 1.3 equals e to the 5r. I can take the natural log of both sides because natural logs cancel out the exponential. Desmos will give me a nice accurate estimate of natural log of 1.3. It's 0.26236. That's probably close enough. And divide both sides by 5. And I'm going to get r equals 0.0524. 0.0524, or about 5.2% interest. And then I do a quick check. Would my instructor give me a question where the interest rate is about 5%? Yes, that would make sense. If you got 28%, that probably wouldn't make sense because there aren't a lot of things that have that level of interest. Okay, one more question, one more idea. So I know that r equals 5.2% gets me from 200 to 260 in 5 years. What would the annual simple interest rate be? And the annual simple interest rate is called the nominal interest rate. Well, it's fairly easy. So here was my actual calculation using continuous compound interest. If I wanted it to be nominal, I would say 260 equals 200 plus 200 times, let's use a capital R this time to represent that it's a different interest rate, but it's still an interest rate. So I simply rewrite as simple interest and then solve for R. Subtract 200 from both sides, and I get 60 equals 200 times R times 5. 200 times 5 is 1,000, so it's 1,000 R. Divide both sides by 1,000. And I get 0.06 equals R. So my nominal interest rate equals 6%. And you'll see this on your worksheet. What is the nominal interest rate that would get you to the same amount? All right, that wraps up this video. Thanks for watching.